This is part 6 of the series Applications of Differentiation. Now up to this point we've been using the extreme value theorem, which tells us that if a function is continuous on a closed interval, then there must be a maximum and minimum on that interval. And it also says that the maximum and minimum can occur at the endpoints, as we've just seen in our previous examples. We're going to look now at a theorem called Rolle's theorem. I believe that's how you pronounce it. And what Rolle's theorem does is it guarantees that the extreme values will be between the endpoints and not at the endpoints. And so let's take a look at what Rolle's theorem says. Let f be continuous on a closed interval, ab, and differentiable on the open interval. This is pretty standard for many of the theorems. And if you recall the reason, continuity on the closed interval is required because we can't differentiate it at discontinuity, and differentiable on an open interval because of the limit definition of a derivative tells us that values have to exist to the left and to the right in order to take the limit for the limit to exist. So that's why we have this closed interval and open interval here. Then, if f of a equals f of b, there's the new requirement. That if f of a equals f of b, then there is at least one c in that open interval ab such that the derivative at c is 0. That means the slope of the tangent line at c is 0. Now just a couple more points before we go on and explore this theorem. Notice that what this theorem is actually saying is that the slope of the tangent line between these 2 points, A and B, the average rate of change between A and B is going to equal the instantaneous rate of change at that point. So you can see that if f of A equals f of B, the secant line is going to have a 0 slope, and this maximum value, or minimum, whichever the case may be, is going to have a tangent line with a slope of 0. So that's one minor point that we'll accentuate later on in a later theorem. And the second thing is that Rolle's theorem is what's known as an existence theorem. It tells us that such a c value exists, but it doesn't tell us how to find it. So we're going to be working on that as well. So let's illustrate Rolle's theorem. So what we're looking to do here is to find the x-intercepts of this function and show that Rolle's theorem applies on the interval between the x-intercepts. So these x-intercepts are going to be our closed interval. So let's go ahead and set this equal to 0. So that's x squared minus 3x plus 2. And since that's a quadratic, let's see if this factors easily. So since this sign is positive, these signs are going to be the same, and they're going to be negative. And so our only options 2 and 1. X squared minus x minus 2x plus 2. There it is. So we know that our zeros, our x is 2 and 1. So there is our endpoints. There are our endpoints. And so we're going to determine if Rolle's theorem applies. Well, this is a polynomial function. Polynomial functions are continuous on their domains, and so the first condition is satisfied, that Rolle's theorem says the function must be continuous on a closed interval. It is continuous, and these values are in its domain, so first condition applies. Second condition is that it must be differentiable on a closed interval, or the open interval. So let's differentiate this. So f prime of x is 2x minus 3. And 2x minus 3 exists at both of those points, so this function is differentiable on the open interval. And so, second condition applies. Now we've got to look at f of a and f of b. So we'll call a 1. So f of 1. We plug in a 1, we get 1 minus 3 plus 2 that's 0. And f of b, which is 2, we get 4 minus 6 plus 2, 0 again. So f of a equals f of b. So yes, in fact, Rolle's theorem applies on this closed interval. So let's go ahead and find out where the c value is. The c value is going to be where the first derivative is 0. So 0 equals 2x minus 3. 3 equals 2x. 3 halves equals x. So our c value is at 3 halves, which is 1.5, and yes, in fact, it is between our endpoints. So we verified what we set out to verify. So let's look at another one. So in this problem, we're asked, does Rolle's theorem apply to this function on the interval -2, 2? If so, find the values of c that satisfy the theorem. Well, the first piece is this function continuous on that interval? Again, this is a polynomial, and so polynomials are continuous on their domain. This is within the domain of this function. So yes, first condition is met. The second condition is that the function has to be differentiable on the closed interval. So let's go ahead and take the derivative of this function. So f prime of x is 4x to the third minus 4x. And if we look, yes, we substituted 2 in here. The function is defined at both of those values. So we're good to go. Second condition applies. Now what we're looking for is f of a and f of b. So we need f of -2 and we need f of 2. So evaluating at -2, put a -2 in here, we get 16 minus 8, which is 8. So 8. And evaluating f of 2, 16 minus 8 again is 8. So yes, f of a equals f of b. So the three conditions of Rolle's theorem are satisfied. So Rolle's theorem does apply. Now we've got to find out all the values where this function is 0. So 0 equals 4x to the third minus 4x. We can factor out a 4x here. So 4x is x squared minus 1. And that equals 0. 0 product rule, we know 1 is 0. So x equals 0. And x squared minus 1 equals 0. So x squared equals 1. X equals plus or minus 1. So -1 and 1. So there are all the c values at which the first derivative is 0. There are 3 of them. So let's move on to the next section now. Now we're going to talk about a theorem that's very closely related to Rolle's theorem, and it's called the mean value theorem. And stated formally, the mean value theorem says if f is continuous on a closed interval and differentiable on the open interval, there's those same two conditions that we've seen repeatedly, then there exists some number c on the open interval such that f prime of c equals f of b minus f of a over b minus a. So let's look in detail at what this theorem is actually saying. F of b is this y value here. F of a is this y value here. So we have 2 points and we've got the difference of the y's. Interesting. And in the denominator we have b minus a. So b minus a. Those are the x values. So here we have the slope. So we're actually calculating the slope of this secant line through the 2 endpoints of our interval. That in actuality becomes the average rate of change of this function across this interval. I hope you remember that ever since the concept of slope was brought up, it was brought up with the idea of rate of change. And here it is coming up again. So again, the slope of the secant line is given on the right side. Well, what's this left side? This is f prime of c. So what we're talking about is the derivative of the function at c. And as you know, the derivative is the slope of the tangent line at a specific point. So this is actually the instantaneous rate of change at a particular point. So the mean value theorem is telling us that if these conditions are met, then the average rate of change of the function can be found by some value c within those endpoints. So the average rate of change is going to be equal to the slope of a tangent line at some point on that interval. Very, very powerful theorem that we're going to use repeatedly. So let's go ahead and see how this theorem applies. So here we're told if f of x equals 5 minus 4 over x, find all the values of c in the open interval 1, 4 such that the instantaneous rate of change is equal to the average rate of change on the interval. So our first order of business is going to be to determine, does the mean value theorem apply? First condition, the function has to be continuous on the closed interval. Well, you can see that this function is discontinuous at x equals 0. But fortunately, 0 is outside our interval. So yes, in fact, this function is continuous on the closed interval 1 to 4. And the function needs to be differentiable on the open interval. So let's go ahead and take the derivative of this function. And before I do that, I'm just going to rewrite real simply just to make it a little easier to see. So this is 5 minus 4x to the negative 1. Okay, now let's differentiate. F prime of x. This goes away at 0. Negative 4 times, well, this is negative x to the negative 2, which is negative, actually it's positive 4 over x squared. That's supposed to be a 4. So there's our derivative. And is this function differentiable on this open interval? If we put a 1 in here, it's defined. If we put a 4 in here, it's defined. So we're good. Second condition is met. So now we know that the mean value theorem does apply. So we're going to look for the average rate of change at this point. So the average rate of change is f of b minus f of a over b minus a. That's going to be f of b. We put 4 into this expression. That's 5 minus 4 over 4, which is 5 minus 1, which is 4, minus f of a, 5 minus 4 over 1, which is 1, over b, 4 minus 1, which is 1. So the average rate of change is 1. And we're looking for the instantaneous rate of change is equal to the average rate of change. So we're looking for where the first derivative, 4 over x squared, equals 1. 4 equals x squared. X equals plus or minus 2. Well, negative 2 is outside of our interval, but 2 is inside our interval. So our target C value is x equals 2. And that is all the values of C that satisfy the mean value theorem, where the average rate of change is equal to the instantaneous rate of change. Now let's look at the next section.